Hello, Vic Broquard here again, Professor 42, bringing you the next in the C++ debugging series. Armed with our basics, we are now ready to tackle the art and science of debugging. And the starting point is what I refer to as my general debugging philosophy. These are the 8 points that are absolutely critical if you're ever going to become good at debugging. And the first one is the one that I've seen more people fail at than any other. It is look, don't think. When you first have a bug, immediately you start thinking, oh, it could be this, oh, it could be that. Well, I know this code should be working, that code should be working. How did I get it? What's going on? Figure, think. Wrong. The starting point is to take a deep breath and look. Observe what is actually there. What are the contents of key variables? Always look and stop thinking about it. The second thing that happens that you need to do fairly frequently is to ask yourself, how did we get to where we're at? This pays particular value when you've got a hard crash, and you can look at the call stack and try to figure out how you got to this particular point. That ranks like number 2 in the sequence. Next, handle only one bug at a time. I know you may have isolated and spotted 6 things that are wrong with your program, but for heaven's sakes, fix one of them at a time. Make sure it's fixed before you go on to the next. On larger programs, debug only one section or portion of the program at a time. That is, to keep your focus on one subset of the program. If you don't, you have a tendency to get completely overwhelmed with the large project at hand, and it will never seem to end. Next, number 5, make only one change at a time and then retest. I've seen too many people make 5, 6, 7, 8, 10 changes and then get an even bigger mess than when they started. And on larger programs, one should keep a log of all the fixes that you make. Why? Because sometimes when you fix one thing, it ends up breaking something someplace else. And by the time you discover it someplace else, you've forgotten what it is that you put in to do the fix, and then you've unfixed the fix, and you get into this incredible morass of fixing and unfixing and fixing and unfixing, and it's a mess. Number 7, if it suddenly starts working and you didn't actually fix any code, it is not fixed. It's an intermittent bug. Keep at it. You'll eventually find the bug. And finally, if all else fails, take a break. Go off, play a video game, have a cup of coffee, go for a hike, do something, and then come back later and look at it with a fresh point of view. All right, given those as our basic philosophy, what are some general guidelines? Well, not everybody has these definitions down pat, so I thought I would go over these. The first one is when you get an access violation. What is it? An access violation is simply your program is attempting to read or write memory that is not part of your program. Typically it's caused by uninitialized pointers or pointers with a 0 value or car garbage in them. That's usually the cause. The next term is heap corruptions. Well, the heap is where things are allocated dynamically, and when you have a heap corruption, it is core that has been, which is part of your program, that has been overwritten by your program. Typically this is caused by subscripts out of bounds, or if you're using pointers as to access array elements, it's gone out of bounds, or general use of pointers. When you get a stack overflow, remember the stack is being used for your automatic storage and parameter storage. And when you have a stack overflow, you've exceeded the size of your stack. Typically this occurs when you're using recursive functions and the function accidentally ends up calling itself an infinite number of times. There are other reasons. You can get a stack overflow as well. You can even corrupt the stack by subscripts out of range, that sort of thing. And finally, memory and resource leaks. Those result from a failure for the program to delete anything that has been dynamically allocated with the new function. Well, with those terms in mind, let's look at an overview then of general debugging. From my point of view, there are basically 4 general cases that you have to deal with in debugging. The first one is what I call a hard fail. This results in a crash, termination, ending of the program. Debug assertions popping up, an actual crash, hard fail, blue screen, that sort of thing. Typically, hard fails are more on the easier side to debug because you know exactly where you're dying, and at that exact point of death you've got in the watch window all the local and automatic storage variables that you can take a look at, and generally they become a little easier to spot why the program died. The second major class is incorrect results. You don't have a hard fail, the program runs. It's that you get wrong output results, wrong behavior, wrong branch taken, that sort of thing. Those are a little more difficult to find because you don't know the exact point where the error is coming from. The next category is a memory leak or a resource leak. Memory leak means you've failed to delete something you've dynamically allocated, like you've asked for a new array, that sort of thing. Resource leaks applies to a Windows program where you've asked for a new brush, pen, font, that sort of thing, and failed to delete it when you're done using it. And the fourth class is an intermittent failure involving any of the above 3. Now, 4 is not really a special case. I just put it in here because I've seen too many people think their program is all done, turn it in, and then when I get the program, I thoroughly test them. And all of a sudden, some strange, bizarre behavior happens. So number 4 is intermittent failures. It doesn't happen all the time. Maybe 90% of the time the program works fine. That does not mean you should put it into production, as some people have done, and 90% is pretty good. Now, intermittent failures are, in my opinion, probably the worst kind of bugs to find. Why? Because most of the time the doggone program was working, and it's difficult to actually zero in and spot the strange behavior that causes it to actually fail for whichever reason, 1, 2, or 3. All right. Armed with this, we're ready to take a look at our program for today. For today's example, I wanted to have a hard crash type of situation to look at, but a relatively simple one to get the hang of it. This time I've chosen a Windows application, but you don't need to know Windows programming to follow along. This should be a fairly simple one, and it is a really dinky, simple Windows application that I've got. The objective is to display a little window with a user font, a particular font in size. The program, when it runs, is supposed to do this. It will show a series of 4 little messages in our chosen font. In this case, it's a standard OEM ANSI font, fixed font on the machine. And if you click the left button, a little box comes up saying you've clicked the left button, and to quit the program you could right click and it asks if you want to quit or not. Real simple program. With a Windows app, there's always an application derived class, but it is basically usually very simple. Creates an instance of it, and part of the creation process initialize the initial instance of our window. Looking at the code for that app class, all it does is allocate dynamically a new instance of our fancy little frame window and proceeds to show it. Our frame window, where all the action takes place, is derived from the Microsoft Foundation class C frame and I've created a bunch of data for our particular window. Has the data been saved yet or not? The current height and width of our window, and importantly for this little lecture, we're going to store the average character dimensions, how big the capital letters are, and the width on the average of the characters and the height. When you're dealing with a variable pitched font, such as Times New Roman, the different letters have different widths. W's are much wider than the I, for example, and when you're displaying things, you need to know the widths of what you're doing. And then for this particular example, I've stuck in the user-chosen font, in this case, dynamically allocated. It'll be an instance of the C font class. Typically, then there'll be a constructor function, a destructor function. The paint function is where we actually display things. And on create is where the window actually gets constructed. And then we'll have a little do you want to shut this application down message if the user tries to close it. Then in the frame window, typically with the Windows application, we respond to messages, and Windows sends, for instance, your program a paint message when it detects that part of your window needs to be redisplayed. And then we'll be responding to left button and mouse button down clicks. We'll be responding to the user resizing the window, wanting to close the window, and when the window is actually being created. And at this point, let's switch over to the program version that's got the errors in it and look at what we've got. In the constructor for the class, the first step was to build the actual window, and I created some fancy little styles for the way that I wanted the window to look, how big I wanted it initially to be, and where it was located on the screen, and then called the Windows functions to create the actual window. Once our window has been created, then I chose to go ahead and put our data saved bool to true and allocated a new font and told it to create an ANSI fixed font for us to use. It could be any user created font at this point. Then in onCreate, I'll call the base class to allow it to build the window, and then I will proceed to get these text dimensions. To do that, one gets a client DC, which represents an encapsulation of the screen, and installs our font into that canvas. We would also install any brushes and pens and that sort of thing that we would want, colors as well. And once we've got our font installed and we're ready to display something, we aren't wanting to display it here. That'll be done when we're given the paint message, but we need to get the text dimensions. So that's done with a function called getTextMetrics. It will fill up a structure with the proper data in it, and then I'll get rid of this canvas. We don't need it any longer, and I'll calculate the average character height and width and the capsule's width from these dimensions. Then on size, I'll simply store our new dimensions. The most important part for us is on paint, where automatically I'll grab a DC, which represents the entire canvas of our window on which we're going to display something. And then I proceeded to install our new user font, pointer font, into the DC and proceeded to call the various functions to display the text. Some of these I decided we ought to have them centered, so I called the text alignment and set it to center, and I text out at the location the width of the screen of our window over 2 and the height over 2, hello from Windows, and then I displayed the average character width, average character height, and average capital letter width, just so we could see what those numbers looked like. Of course, then if the buttons were pressed, I displayed a little message box that you've clicked the left button, and then proceeded to change the bool data save to false. Presumably, if this was an editing type program, if you change the data, then data hasn't been saved, that sort of thing. And if they click the right button down, I'll send a message that we want to close the program, and when we close, I'll pop up a little message box. If the data has not yet been saved, I'll say, hey, do you really want to quit? Instead of just automatically shutting down and letting the person lose any of their changes. So we'll just play a little game there, and then if everything is okay, we are going to terminate, forward it on down to the base class frame windows on close. looks like a fairly simple program. So let's run it and see what happens. When I run it, boom, crash and burn. In this case, you're getting a much better crash and burn than we used to. In the old days, at this point, it was a hard crash and burn fail. But as time's gone on, Microsoft has gotten better and better and better at trapping some of these dumb errors that we users have made. And in this latest version, .NET 2010, they have really improved things remarkably from that old hard crash where you wonder what the heck is going on. Now we've got an unhandled exception. Something about a context being deactivated. You go, what? And we're in some kind of very strange place. Well, let's do a break and stop and look over here at our call stack. If we look at our call stack, we are in the MFC Dynamic Link Library, the DLL, executing obviously Windows code. But let's back up. How do we get to wherever we're crashing? Well, we got to there from here, from line 46. Line 46? Line 46 is the next thing to be executed. So if we back up, we're dying here. We called the create function to build our window. We have not yet gotten back to the code down here. But if you recall, when I first ran it, I triggered a breakpoint. Let me stop and show you that again. Follow along. Start debugging. The first thing that happened is true. In our constructor, we created our initial little variables and passed them to this create function to build our window. But in the building of the window process, Windows came back to us and said, hey, it's create time, and he sent us a WM create message telling us that now is a chance for you to do any additional creation things you want to do. Step one was I called the base class and got it to build its portion of the window. And then I'm about to go ahead and get a canvas on which to display, insert our font, and get the text metrics. And so when I hit debug again, continue, boom, we died. So, how did we get here? Well, we're dying here in onCreate, but onCreate was called from create up in the frame window, and if it had succeeded, we would be here ready to set data saved equals true and allocate a new font. Wait a minute. What are we doing down here? We're trying to insert a font that doesn't exist and then trying to get metrics on it. Well, no wonder we crashed. It's an out of sequence event. So what we really need to do is move our initial data from here up to the start of our constructor. And this is a good takeaway. Always allocate your class member variables that you can before you start calling into the Windows functions that could potentially use them. I will stop this debug and start it again and see what it does. Well, here's our breakpoint. Again, I'll remind you, we allocated our font, then we called create the window. Create the window called back to us with a message. The window is about to be created. Make any changes you want. We allowed the base class to actually build the Windows portion, and now we're ready to allocate, hopefully, our average character dimensions. Well, I'm just going to turn it loose and see what it does. How about that? It's working. We got our hello from Windows with our right font, character dimensions, 8 pixels wide, 13 pixels tall. We can resize the window. Of course, every time we resize the window, he has to call Paint to redisplay the contents. I can click my mouse buttons and quit. In this case, I right clicked, terminated the program. And all is well until you look at the output. Look at the output. Oops. One of the nice things with the Windows app, it automatically detects memory leaks. And we've got in this case, a resource leak, or memory leak, however you want to look at this, and it's 8 bytes long. What's being leaked? Well, as I said earlier in the start of this 4th lecture, resource memory leaks occur because you failed to delete something that you've allocated. Well, if we back up here to our constructor, we allocated a font, and that's what's being leaked. Nowhere did we delete it. So when our program terminated, we leaked and failed to give back to Windows the font object that we had allocated. How do you fix it? Well, there's a number of ways of doing it, but the easiest way is to take care of the deletion either in your destructor or when the window is being terminated. And that can be easily done by using what's called the class wizard. In class view, I've selected the frame window class. I'll invoke the class wizard. It comes up. I happen to know in this case that we need to add a new message. We need to be notified when the window is about to be destroyed, so we can go in there and delete our font. So I'll select WM Destroy as the one I want, and I'll click Add Handler, and he will automatically add that one and add the prototypes, the message handlers, the whole bit. And so in frame win down here, if we're going to destroy the window, at this point I will go ahead and delete our font. Go ahead and delete our pointer font that we had allocated. Reminding you again, up here we said I want a new C font, so down in Destroy I'll delete the pointer font. Notice also that the wizard added the appropriate messages where we were needed. Makes the class wizard is really nice for adding known things. Now I'll start it, run it again, let it build. And resize the window a little bit, make sure it's still working fine. And I'll terminate, and we'll go down here and look, and Viola, no more resource memory leaks. So this was a relatively simple example, but I wanted you to have a chance to see what a hard crash looks like in a Windows application, and to see an easy to spot resource memory leak. Now that we've got our principles down, in the next lectures we'll start looking at more complicated debugging situations and put these to use. I've had some requests that people would like to be able to see these examples and play with them, so in the future look for all of these debugging lectures and the sample programs with the bugs in them for you to play with, as well as the good version in case you're having trouble finding the bugs, up on the website. But give me a few days and it'll be out there. Thanks, and see you next time.